Okay, so now let's look at a phase diagram. This is what phase diagram? Iron carbon, the most important phase diagram that mankind ever studied. For chemist background, maybe you don't appreciate that much, but for anyone who study material, this is the most important phase diagram. The so-called steel age, from stone age to brass age to so-called steel or iron age, based on this. The human tools, all the human mechanical tools, I wouldn't say all, but the vast majority are based on what types of material? Iron and steel, right? Automobile body, automobile chassis, your wrench, your knife, and your screwdriver, and almost every major tool are made out of steel. That's why it's the most important phase diagram for mankind. So let's review our knowledge a little bit. This is binary or ternary phase diagram. Binary means it has two components. We can view it in two ways. One is between iron and carbon, or in this case, we can view it between one side is pure iron and the other side we can treat it as so-called cementite or iron 3C. Iron 3C. We can kind of call it a pseudo binary phase diagram. Okay? And L means liquid phase, which means if the composition is from this 0 iron all the way to 6.7 iron, if the temperature is above these lines within this single symbol, the system would remain as a liquid. Single phase uniform liquid, whether your temperature for the same composition, whether you are here or you are here, or at the same temperature, whether you add a little bit more carbon from here to here to here, it's the same single phase. What's the analogy? The analogy would be, okay, you have a cup of water, pure water, liquid, single phase, right? When you add just a little bit of sugar, dissolve it, what is that? Completely dissolve the sugar, what is that? Still single phase, right? Transparent, the sugar dissolved, still single phase. That's it like this. But then once you add a little bit of carbon, not carbon, the sugar into the water, now you have at least two so-called component or two substance. One is water, H2O. One is sucrose or sugar, table sugar. Make sense? But they together form a single phase if you uniformly dissolve it. Make sense? This is so-called single phase region. Anything in the phase diagram that has one symbol means it is single phase. L is for liquid, and this guy called gamma austenite, that is a so-called single phase solid solution. Let me ask you this. If I'm at here, what does that mean? Single phase, is that pure iron? No. It has roughly, if you read down roughly, if I point into here, roughly 0.7%. The horizontal axis means composition, weight percent of carbon. The vertical axis is temperature. So it's a composition temperature graph. And in this point, I'm at roughly 0.7% weight of carbon in iron, but it's gamma, which means it's not a liquid, but it has only one symbol. That means it's a single phase so-called solid solution. Single phase, which means you look at that solid piece of material, it looks physically and chemically uniform. You don't find one section denser than the other section. You don't find one section that is harder than the other section. It's pretty much the same composition, same crystal structure, same density, same hardness throughout. And for that, if I raise the temperature a little bit, same composition, raise the temperature a little bit, I'm still at so-called single phase region, right? Or for this one, if I add a little bit more carbon, I'm still in the single phase region. Okay, what about here? That's a plus sign, gamma plus what? Fe3C, right? That means this is one phase or two phase? Two phase region. One phase is what we call gamma phase. The other phase is this guy, iron 3C, which is so-called cementite. Now what it means? It means if my system composition, let's say roughly 4% at 1000 degrees C, the material looks uniform or non-uniform? Non-uniform. You will look at it, it looks like it will be a so-called two-phase mixture. Some portion is the gamma phase, softer, denser. Some phase is the iron 3C phase, those darker, brittle, lighter phase. Make sense? Two phase mixture. When you look at, if you have a way to look at that stuff, it doesn't look uniform. Two phase, just like oil and water together. Make sense? Or in another way, just like powders of copper and powders of, let's say, silver mixed together at room temperature, not uniform. Make sense? That's phase diagram. And here is another single phase or two phase? Two phase region. One phase is, as we labeled, alpha phase. It's another crystal structure of iron. Soft, reflective, highly conductive, dense phase. The other phase is still this guy, iron 3C. Brittle, hard, lighter phase. Not uniform. But this is what a phase diagram look like. Phase diagram is a diagram, temperature composition diagram, that tells us for a given composition, for a given temperature, what are the phases there and what are the composition of the phase there. Right, that's what you learn in thermodynamics, in phase diagram. And actually, if I'm here, the two phase, one phase would have the composition here, the other phase would have the composition here, the so-called tie line rule. And the relative amount is what you learned in your physical chemistry or thermodynamics, so-called level rule. Make sense? Or let's refresh our mind a little bit. If I'm at here, roughly 800 degrees C, 2% of carbon in iron. How many phases? Two phases. One is gamma, one is iron 3C. The gamma phase composition would roughly be what? If you eyeball it, the gamma phase composition would be what? If you eyeball it, it will be the horizontal line cross this phase boundary. That gives you roughly 1 weight% of carbon in iron. That is your composition for the left gamma phase. What's the composition for the other phase, gamma Fe3C? It's given here, 6.7 weight% of carbon in iron. And let me ask you one question. For here, just one question. If this is my system, this is my temperature, at here, which phase is the majority? The gamma phase or the iron 3C phase? Well, that's what your level rule learned, right? The level rule tells you, okay, it's by the ratio of so-called the left arm versus the right arm. The left arm versus right arm, which means, okay, the relative amount of gamma phase would be the opposite from here all the way to here divided by the total difference. So here, if this is my system, 2 weight% of carbon in iron, the gamma phase would be more than 50%, while the so-called cementite or iron 3C phase would be less than 50%. Make sense? Let me ask you another one. If I'm here, 3%, 1200 degrees C, how many phases? Two phases, one would be gamma, one would be L for liquid, and which phase is more than 50%? The L or the gamma? It's a level rule, right? For the gamma, the left one would be the opposite, divided by the total. So the gamma would be from here to here, divided by from here to here. So the gamma would be less than 50%, while the liquid is more than 50%. Questions? Okay. Okay. So let's resume our class. First portion, the very basic introduction. We talked about the kinetics and phase transformation, and we said it's linked with thermodynamics, and it's important. So we are going to talk about a few examples. One is the last time we talked about the iron carbon phase diagram, right? Then we reviewed the phase diagram a little bit. Now let's look at some practical experimental data. Not precise, but the semi-qualitative data. What we are looking at is hardness, how hard a material is. For steel, a type of steel, iron carbon alloy with pretty much all iron with a very small bit of carbon. Okay. And for steel, we tested the harness using diamond or some other steel ball to press into it for harness, and we measured versus a processing parameter, so-called cooling rate. Cooling rate is after we process the steel, we are going to cool the material down from processing temperature, 800, something like that, to room temperature. And with this cooling rate, we can have different cooling rate. Some of them can go very high cooling rate, like 1000 read the unit degree per second. This much, going from 1000 degrees C red hot to room temperature. Typically, you achieve that by so-called quenching, whether in water or in oil slightly. On the other hand, we can go to the other extreme, 0.01 degrees C per second. Roughly 1 minute 2 degree. 1 minute 2 degree, which means from 1000 degrees C all the way to room temperature, we are roughly talking about 500 minutes, 8 hours. 8 hours to cool from 1000 to room temperature. That's typically so-called cooling together with a very big furnace, or even controlled cooling. You don't shut off the power right away. You let it gradually cool. Of course, you can have something in between, from between quenching, throw the red hot metal into water, versus you heat during the cool. You lower the temperature gradually, but in order to prevent it to cool too fast, you are continue heated, so that you have a very controlled slow cooling. And for people who study metals, they noticed a very important phenomenon, as what we show here. People observed for the same material, steel, which is iron carbon alloy, with the same 0.4% weight percent of carbon. Okay, the same material composition, but by cooling it in different fashion, what changes dramatically? The so-called hardness, right? People observed, and actually people know this for thousands of years. The ironsmiths know this for thousands of years. When they cool that piece of steel slowly, gradually reduce the heat, the hardness you got is actually very low, 100. This number is pretty low. It's like your typical can, tin can for canned food, of a typical clip, paper clip. Those type of metal, which is steel, you can bend back and forth, it's relatively soft, or for the so-called pipe cleaner, those types soft things that people use for craft. On the other hand, go to the other extreme that people ironsmiths quite often use is when they drop that red hot metal into water or into oil, the hardness is much higher. And for this, people can use it for knives, for hammers, those type of tools that you really need high hardness, especially for knives or for saw. For knives to cut, you need the hardness to be high, otherwise it quickly becomes blunt. Make sense? Or for chisel, you need those things to be hard. And of course, you get something in between if the cooling rate is in between. This is one aspect in terms of, okay, material science relatively is very different from chemistry, pure chemistry. For chemists, once they know the phase diagram, that's pretty much it. Chemists no longer touch the problem. But for ironsmiths and the later material engineer, okay, they study this and they want to understand. And what people find gradually over time, initially they got the empirical relationship. And later on with the appearance of microscope, now people can look what is going on. I haven't changed my composition. I didn't add more carbon to it. Well, they find, okay, when the cooling rate is low, you got so-called the spheroid. Essentially, you have this sphere type of structure. Okay, and when they increase the temperature a little bit, cooling rate a little bit higher, they find, okay, we have so-called pearl light. If under a colorful polarized light under optical microscope, you can see really like a pearl. They look like colorful reflection, not just a pale white like metal, but colorish that reflects fine microstructure. And sometimes you see here those so-called closely interspaced structure. Closely interspaced structure, and we show here lamella. You see here one layer, another layer, different shades or different color. Pearl-like structure, and it has higher hardness at a higher cooling rate. And then when the cooling rate goes a little bit farther, the microstructure changes further. And to some extreme case, you see people call this laced structure. Sharp, kind of needle or plate-like structure, very dense, extremely dense. And people call it so-called martensite structure. So, what people observed empirically is by changing material cooling rate, which is processing condition, we can change microstructure. The changing of cooling rate, which is processing, right? Process. How do we process the material? Would change its microstructure. And the microstructure, later on, people realize it is the microstructure that determines the material property, and in this case, hardness to a large extent. Okay? And what we learn in this course, the so-called kinetics and phase transformation are critical to processing. How fast we process, right? How fast? Cooling rate, that's a rate thing. How fast we control the process determines the microstructure, and the microstructure determines, as a result, the materials property. And this course, we are going to have some more understanding of this process. How does the processing changes the so-called phase transformation, changes the microstructure development, and as a result, the material property.